Hi, everybody. I wanted to go over arc length again. We talked about it in class today, and I didn't really explain part of where the formula came from, and I kind of wanted to. So the idea here is that I want to know the distance between this point and this point, and I would like to know the distance between those points along this curve. But the problem is I don't know how to find a distance along a curve. I know how to find distance of segments. So I can find the distance between these points if I wanted to, because I know the distance formula, or I could imagine that as a triangle and do the Pythagorean theorem. But I mean, you can tell from that segment that this segment that goes straight across here is not a very good estimate for this distance. There's a lot of difference between the two. So if you do what they did in the picture here, and instead of just making it one big segment, you make it 4 smaller segments, well, now you're getting better. That would be a much better estimate for the distance, but you can see it's still not perfect. There are still gaps in there. So what made this 4 segment answer better than the 1 segment answer? Well, the smaller the segments get, the closer they are to estimating the curve. So if instead of 4 I were to use 8 or 16 or 32 or 64, or, almost like an infinite number of segments, then that would give me the best estimate for the distance along that curve. So how can we do something like that? Well, we know that, you can probably already tell that we want the distance between the segments. We want the change in x to be as little as possible. And how could I also use what I know about geometry to find the length of that segment? Well, this is a squared, or that side is a, that side is b. But if we're talking about coordinates, this side is the change in x, and this side is the change in y. And so according to the Pythagorean theorem, a squared plus b squared equals c squared, but that would be c squared equals change in x squared, that's how long this is, plus change in y squared, that's how long this is. So that's kind of like a different version of the Pythagorean theorem. So if I were to take this a squared plus b squared equals c squared, but in terms of change in x and change in y, then this is what I would get. I would have the distance equals, not c squared, c, because we took the square root of both sides, change in x squared plus change in y squared. Okay, so if we look at this, this would be c squared equals a squared plus b squared. So what they've done first is they factored out a delta x squared. So why would you do that? Well, it's a really weird thing to do. There's a purpose for it. We'll get to it in a minute. But so far, can you just agree that if I were to distribute that delta x squared, I would get the same thing that I started with? Well, yeah, I can tell that those are the same thing. So, okay, weird thing to do, but all right. I can see how that would be equivalent to the original, to what we originally started with. Okay, so all that's happening from here to here is I'm going to take the delta y over delta x, and I'm just going to make it one big fraction. Instead of 2 individual terms that are being squared, I'm just going to make it one term and square the whole thing. So that's all that happened to get to here. So now what I need to do is, instead of finding all the c squareds, because remember this is still squared, I want to find all the individual lengths. So that means I need to take the square root of the individual segments. And then I want all of them together, so I need to add them all up. So what we've got here is the sum of the individual distances of each one of those little segments that go from one end of my curve to the other. But we can simplify this a little bit more. Sorry, my dog is playing with her squeaky toy right now. We can simplify this a little bit more because we've got a squared under a square root. And so the squared and square root, we can at least cancel that one out. Now, we can't cancel the other one out because it's got addition in it. So changing y over changing x, like that's like changing y over changing x, like rise over run. Oh, that's really just slope. So that's really just the slope squared, but wait, we're in calculus, not algebra. So slope is really the derivative. So hopefully that made this a little bit easier to follow from one end to the other. But basically what we did is we took, oops, didn't mean to erase that. We took the Pythagorean theorem, we wrote it in a way that was a little bit weird with delta x and delta y instead of a's and b's. We solved for the length of an individual segment, and then we added all of the individual segments together, and then we rewrote it using a calculus notation instead of an algebra notation. That formula is never going to change, and the reason it's never going to change is I didn't just assume that that function was any particular function. I didn't work this out assuming that the function was x squared, because if I did, it would only work for x squared. I didn't work it out using any particular f of x equation. So this is the general form for the distance between 2 points along a curve, and it's never going to change. So you've got to add up. There's the calculus version of add up all of the individual distances, and that gives you the total distance. So when we look at these problems, you're doing the same thing every time. It's always the integral, it's always the square root, it's always 1 plus the derivative of your function squared. So for this one, the derivative of 4x was 4. So there's our f prime. 4 squared is 16 plus 1 is 17. So we need to do the antiderivative of root 17. That is x times root 17. Plug in 3, you get 3 root 17. Plug in 0, you get 0. So 3 square root of 17 is it. And then if you look at this next one, it's a linear function, but again, from -1 to 2, square root 1 plus, what is the derivative of 5x minus 2? Well, it's 5. So 5 squared is 25, plus 1 is 26. So we have the integral from -1 to 2 of square root of 26. Antiderivative of that is x, square root of 26. Plug in the 2, plug in the -1, and subtract. So it was minus a -1, and that's the distance between those 2 points along the line, in this case, 5x minus 2. This next one is a little bit, it's the same thing, but it might seem a little bit more challenging because it's all in terms of variables, no numbers in it. So I want the exact length of the distance between 2 points between A and B and this is a linear function. So that would be the distance, the integral between A and B, square root 1 plus, the derivative of mx plus b is just m. So you would get square root of m squared plus 1. Those are all constants, by the way, so that's just a number, some number. The antiderivative of a number is that number times x. Plug in b, plug in a, and subtract it. So that, I don't know that that form of the answer is any better than this other form of the answer, but either of those would be an acceptable answer for this particular problem. This one we went over in class. This one was not so much calculus challenging, I don't think, as algebra challenging. So first of all, if f of x is x to the 3/2, then the derivative is going to be 3/2 x to the 1/2. So we've got integral from 0 to 4, square root 1 plus, that's always going to be there. And then we have our derivative squared. That step is calculus. Then we've got some algebra to do. If I square 3/2 and square x to the 1/2, then I get 9/4, and 2 times 1/2 is just 1, so 9/4 x. And I need to be able to simplify this, but I can't do the square root when things are added together, unless I can rewrite it as something squared, which doesn't look very promising in this case. So I either need to be able to simplify this so that I can do the square root of it, or I need to treat this as u substitution. So if I let u equal 1 plus 9/4 x, then du would be 9/4. Well, I didn't have a 9/4, so I put a 9/4 and a 4/9. So now we have the square root. This is essentially the square root, u to the 1/2 du. And then the antiderivative of that, add 1 to the exponent, divide by the new exponent, and then evaluate that from 0 to 4. So the rest of this is just some kind of messy plugging in numbers and simplifying things. If you guys got to this point, the one that's highlighted right now, I would be okay with that. That is equivalent to the other one that's written here, but if you could get to the highlighted part, then that would be fine. Just a reminder, the 3/2 power really means the square root of your base cubed. So just a reminder in case you ever need to use that. So number 5, I want to know the total distance that this bug has traveled. I'm going to leave this one. We talked about it in class today. I'll go through it real quick. But this is just a whole lot of algebra. I've got a function. I did its derivative, and then I simplified its derivative. So its derivative is x times x squared plus 2 to the 1/2 power. So integral square root 1 plus, there's the derivative, and there's the squared. So those terms inside are being multiplied together, so I square the x and square the base with the 1/2. That becomes x squared and just x squared plus 2, because 2 times 1/2 is 1. If I distribute that, then we get all of this. And what I said on the last one is, at this point, I either need to be able to simplify the square root of that expression, or I need to do u substitution. Well, if I let u equal x to the 4th plus 2x squared plus 1, that part in the square root, du is going to be 4x cubed plus 4x. And I don't have any x cubes or x's floating around outside that square root sign. So u substitution in this case, getting du would be pretty much impossible. So there must be another way. I can't look at this, as u to the 1/2 because I don't have all the pieces I would need for du. But if you look at this, those two expressions are equivalent to each other. What multiplies to 1 and adds to 2? Well, 1 times 1 is 1, 1 plus 1 is 2. So this is like a different version of a trinomial. And now that I can write this as something squared, the squared and the square root cancel out, that I can do the antiderivative of. Get 1/3 x cubed plus x, plug in the 6, plug in the 0, and subtract. So the total distance that this bug traveled is 78. And it said average, so it traveled 78 feet over a 6-second time period. So that averages out to 13 feet per second. The last ones, I didn't get time to go over these in class today, and you have 2 on the homework that are like this. these are calculator problems. So all of these others you should have been able to do without the calculator, especially since it said find the exact answer. But these say evaluate using a calculator. So on the homework, I need you to be able to set up the integral, and then I need you to be able to work it out using the calculator. So if the function is e to the x, the derivative of e to the x is itself. So we have square root of 1 plus, and then there's our derivative squared. And then you just go to the calculator and you type this in. So, let me open my calculator. You go to math and you choose number 9. And I need the integral from, sorry, let me get my split screen. The integral from 0 to 2 of square root 1 plus e to the 2x. You could write that as e to the x and then a squared outside, but that's the same thing. And then when you hit enter, that's it. So on the ones that say use a calculator, you've got 2 fill in the blanks, one to write the integral and the other to type in the answer. And hopefully that gives you enough information for you to be able to work on the homework. I don't know when we'll be back, if we'll even be out tomorrow, or who knows what'll happen with the weather. But I wanted you to have enough information that you could have a decent chance at doing the homework without struggling too much on it. I will say on the homework, I'm going to add a video on number 2 specifically, because number 2 is different with the absolute value. How do you do the derivative of absolute value? Well, there's kind of a little trick to it, but I'll do a separate video for that, and I will attach it to problem number 2 in the formative. So I hope you guys have a great evening, and if we're out for weather tomorrow, then y'all be safe and stay warm, and I'll see y'all whenever we get back.